Okay, so it's time for another project. This time we're going to build a function generator from some parts. This is a cavity oscillator. It does from 500 kilohertz to 530 megahertz. You can change the frequency with this knob, and you can fine tune it with this knob basically. Okay, this has got two outputs and it takes minus 5.2, ground, plus 20 and minus and plus 19 volts to work with this, to make it work. I've tested this and it's working fine. Second thing I've bought, it's this modulator and amplifier. Later on I'll open this and I'll go into details of what they inside of it and what it looked like. Okay, this is good for 1 gigahertz, the amplifier, up to 1 gigahertz. It's got input output, and it's got input output for the modulator bed and for the amplifier. This takes plus 44, minus 5.2 and plus and minus 20. That's that. We got a mechanical attenuator. It's quite stiff. I'll go from here. I will open this and show you what exactly is inside. So got that, and last but not least, we got the divider and filter assembly. And this, obviously, the divider bed is mechanical here at the bottom. With this, it's got switches inside, so you can just switch between ranges. Okay, and this takes minus and plus 5.2, and it's got ground, and it's got the oscillator input. We got the filter output, we got the filter input, and the oscillator output. Okay, and I've got a lot of these connectors basically to connect the various blocks together, basically, so the signal can travel from the beginning to the end, basically. So I've decided to build a function generator because I do have function generators. I've got two of them, but they only go up to one of them go up to 10 megahertz and the other one go up to 5 megahertz. I want to have something that goes more than that. So if I can make this work, this function generator can go up to 530 to 540 megahertz. Alright, so I can't really open this to show you what's inside, but it's got a little amplifier here and got those what's inside this. I don't want to go into this, mess it up. Obviously at this type of frequencies, when you get over 100, 200, 300 megahertz, this is the type of oscillators they use. They don't use crystal oscillators. So that's that. Let's get into the amplifier. Okay, as you can see, there's a lot of screws around because this can go up to 1 gigahertz. You need to be able to basically not let any signal come in or go out to interfere with the actual amplified signal. You don't want any noise to come in, or you don't want any signal from other section of the device to get coupled into the output or the input of the amplifier, basically. So that's why you got so many screws, and you got, as you can see here, you got this mesh, basically. You got this. Oh, and I dropped the screw inside. Okay, so you can see this is the amplifier. This section is the amplifier and this section is the modulator. You can see they got some weird ass gold-plated weird transistor or driver or whatever this is. So signal comes in, RF comes in, RF goes out, RF comes in, RF goes out. As you can see here, it does have it's got stuff written on it, so you kind of will know what the voltages or what these wires and inputs do. So you got plus 44, you got detector, potentiometer, you got plus 44 again there, you got RF out, RF in, you got bandwidth limiter, you got 5.2, you got minus 19, plus 19, and you got the modulator output. Okay, so that's that. Okay, just put it here. Okay, I don't think I need to change anything with this. I don't need to modify anything in this. I've tested this again. I've fed the oscillator input into it, and it works perfectly fine. the amplifier bit. I haven't tested the modulator bit, but I don't think I need to. There's hardly anything inside this bit, but let's just check it anyway. Here, you can get optional boards to put inside here. Again, you got the connectors here for the supply voltage, and it's all been indicated. So you got plus 44, you got plus 20, you got minus 20, plus 5 volt, minus 5.2. So I don't need this bit, this section of it. Okay, so that's that. I was thinking of changing this whole box. I mean, taking the amplifier out and putting it into another maybe enclosure or something. But then again, the amplifier does get hot. Those two drivers, chip that you saw, the devices you saw do get pretty hot because this runs on plus 44 volts. So I might leave it as it is. I mean, they built this like this for a reason, so I might just leave it like the way it is. Might not change anything. The only reason is because it's quite bulky and heavy, so the enclosure that I'm gonna have needs to accommodate for all of this stuff. That's the attenuator. Let's see what's inside this. This is a mechanical attenuator. You can see here. Okay, I'm not going to open the bottom. There's a lot of screws here. Basically what it is, as you can see here, these this shaft are controlling the little metal gears at the bottom here, and the metal gears are pushing at the bottom, are pushing I think switches into the PCB where you got an array of precision resistors to basically attenuate the signal as it goes from let me see, as the signal travels from this end to this end, this end to this end. Basically there's a resistor network basically to attenuate the signal the way it's either connected to ground and through the signal. Basically that's how attenuators work. So if I don't use this, I might salvage the precision resistors that is in it. Okay, that's this. I think I tested this and I think it did have an issue, I think, and I think until the attenuations, I think they weren't working properly. I think they were quite noisy, so I'm not going to use this anyway. I've got if I can get it here, I've got down here, and I've got this too, and I have this, and this. Now what are these? These are, as this was a mechanical attenuator to attenuate the signal from your function gen, these are digital attenuators. So you got the signal coming from this and you got the signal going out this way, and the way this is controlled, it is wire here. As you can see here, you feed it the digital signals. I think it's 4-bit, 4-bit digital signals, and you can, according to those digital signals, you can attenuate the signals. As you can see here, you got the precision resistors here, and you got the relay that's switching between which set of attenuator you want. So I got this. These two are exactly the same as that, but these are got 4 different attenuation basically. You can see it's 11 dB selection, and this is 100 dB selection. Again, these are another attenuators. I think one of these ones got issues. I don't know which one it is, but these are, again, you got signal coming here, you got signal going out, and in between there's a lot of relays in between. If I pull this out, there's you can see the relay connections here, here, and these are the driving basically for the relays, and this attenuates the signal as well. I don't know how many dB this does. It's not written on it. And then we got this one as well. I might open this and show you what's inside. You need to be really careful with these electronic attenuators because even just opening them up and playing around with it, with the dirt on your hand, you can compromise the accuracy of the attenuators basically. As you can see here, let's see. There we go. So you got 2 relay, 4, 6, 8 relays. You got the signal coming in here, you got the signal going out, and you got auxiliary signal going out, and you got the driver transistors for the relays basically. And what you got at the bottom is a signal. As the signal is traveling from here to the end basically, these relays will basically turn on or disconnect or switch between, like, connecting or disconnecting the PCB path through a set of resistors and capacitors, and that way you can attenuate your signals basically according to whatever setting is, whatever dB is being set in here in the manufacturing process. So I don't know how many dB this one attenuates the signal to. I don't know if it's written here anywhere. No, unfortunately it doesn't say how many dB it does, but I can test that later, it's not an issue. I just wanted to show you what's inside this. This is an HP part basically, so as all the other stuff that I have are HP part as well, so I might use this. So I can just close this. Okay, I'll close that to screw later. So that was the attenuator section. Just get rid of this and get rid of this. Then we got this, which is the divider and the filter assembly. I'll just put this here. Again, this got a lot of screws, as you can see here. Again, because the frequency comes into here, and you got the filter section and you got the divider section, you don't want the frequency to get coupled into anything else. So here's the divider bed. Basically you got the power coming in, you got the dividers, you got the counters basically to deal with the division of the frequency. So you can see here you got 5 to 1, 1 to 2, 2 to 4, 4 to 8, 8 to 16, 16 to 32, 32 to 64, 64 to 1 to 8, 1 to 8 to 256. That's the division ratio, I believe. It's been written on the PCB. And if I remove this, oh no, we got another one here. As you can see here, you do have some custom made HP IC, so if any of these blows, then that's it, you're buggered basically. Even these ones, you might be able to find, they got some weird ass part numbers, you might be able to find what they are. I think all of them actually are like that. Yeah, so they probably are just like some custom chip. These are custom, I know, because you can tell, but these are probably some TTR logics, but you might be able to find what they are through the service manual. So you can see here again, you got this big massive ground plane there to touch the ground over here basically, so you don't get any coupling basically of the frequency jumping around. And here is the filter section. So you got the filter by variable capacitors, a lot of caps, and you got a lot of inductors basically, chokes basically. And here's the where you attenuate the signal with this rotary switch. As you can see, as I'm switching it, these plastic things are moving around basically, and what they are, they just switching. There's tracks, gold tracks on the PCB, and these plastics, they've got the gold contacts at the bottom, so each turn you turn, individual switch gets basically activated or deactivated through the PCB. Lovely piece of kit. So this is the filter section. Basically what happens is once you feed the signal into the divider, your sinusoid the signal into the divider. Once it gets divided, the output, it comes as a square wave. It doesn't come as sinusoidal sine wave. So what you need to do, you need to run it through your filter again, remove the harmonics and remove all the unnecessary bit and turn it back into sine wave again. So that's what it is. You got the counter, the signal comes into the counter, gets divided and then goes into the filter, gets converted into a sine wave again, and then goes out to the amplifier basically. So that's why you need, okay, I can put this here. That's why these two are connected together next to each other. So that's what I wanted to show you. Now I've tested all individual parts of this and they're all working okay. This takes plus or minus 5.2 and it's got a ground. Doesn't go here. There we go. So as you can see here, it's got this metal shield all around it here basically, because this can divide up to 1 gigahertz, and they don't want any coupling or any signal running around basically causing any problem. So that's why you got so many screws and everything. They need to be tightened properly. So I didn't tighten that one. So that's that, and you got a reverse power protection basically. So once you get the oscillator signal going into here, then you got from here going into the RF in of to the modulator, and from the output of modulator it goes into this, and from output of this goes into the RF in of the amplifier. From the amplifier you take into your attenuator if I'm using this or whatever I'm using, and from the attenuator it goes into RF in of here and the RF out of here. Basically this little section here protects everything else. If you feed in, unfortunately, if you put in your function generator into a test circuit, and that test circuit is all of a sudden gets shorted and is sending signal or sending current back into your function gen, you don't want anything to blow up. So that's why you got this protection here. This takes plus 5.2, and it's got ground for everything of the body of all the equipment. They're all grounded, so I'm going to use the ground to connect basically to the body, because you don't see any ground anywhere else. There's no ground. There's no ground input anywhere basically. I mean, like those go plus and minus 5.2. There's no ground, so the ground is the body of the actual part that I'm using. So that was that, and last but not least, we got the counter, and it's got the, I think it's 1, 2, 3, 4, 5, 6, 7 or 8 LED displays. As you can see here, again you got those weird ass HP custom made chips, and this is a counter. This does count up to 512, I think 500 or 600 megahertz, but unfortunately this ones that I have aboard of eBay, it counts only up to 45 megahertz. I think there's a problem with the pre-scaler. I think there might be something wrong with it. So you got the LED drivers, you got the counter and the decade counters ICs, and you do have some 74 LS logics here. You got some weird ass numbers again, ICs. I think these are the LED drivers, and you got your crystal oscillator 5 megahertz for the time base, and you got your input, digital input here, and you got your 3 inputs. You can either input one is for the signal input, so you can count it, basically you can measure the signal, and I don't know what's the other 2 for. And then here you got internal, external, and you got down here again, and you got times 10 and times 100. So your basically decimal point jumps around when you're choosing that. I'm not 100% sure if I'm going to be using this, or I might make my own counter. I might use the circuitry of this and just change the LED display, because it's quite small, the LED display. I might change it into next tube as I did in my previous videos. That's for Oscillator project. So first I need to fix it If I can fix it, then I can decide what to do with it. And the last thing I need to do, this whole project, all the equipment, the voltages they need is plus or minus 20, plus or minus 5, and a plus 44 volts. So I need to make my own power supply using this and this transformer. I have tested the circuits, and the plus 44 doesn't take that much. I think it takes when I tested, I think it takes about 500 milliamp. The plus or minus 5.2 takes about 1.5 amp, and the plus or minus 20 volt takes 1 amp. So this transformer, I've tested it. Great, it does the power that I need, and I'm gonna be doing make a I've forgotten that linear regulator. So I'm using my 2N3055 as the pass transistors. I'm going to be using Zener diodes, a couple other transistors, and these transistors to make a voltage regulator, basically. The voltages that I have here and the voltages that I need here. For the 5.2, my voltage for the transformer is running at 10 volts, so it gives me enough headroom. Because once I'm pulling 1 amp or 1.5 amp, obviously the voltage of the transformer is going to drop, so that'll be fine. The 20 volt, I'm getting 24 volt on here, and the 44 I'm getting 47. So this transformer is perfect, and the fact that it's a toroidal transformer, even better. Bonus, takes less space and more efficient than normal transformers. This is the transformer that I got off eBay. I think this is for the HP, I think the equipment that I bought. As I said, the guy, I think dismantled function generator, and it was just selling the parts, so I bought all the parts basically for it. He said that there was issue with the device, so he dismantled it to sell it as a scrap. I bought this, but I'm not going to be using this. It's quite heavy and bulky, so I'm just going to use my toroidal transformer. So I need 2, 4 and 5. I need 5 rails for my power supply. I've got the capacitors to run for the power supply. For the 44 volts, I'm going to be using 39,000 microfarad, 75 volts. Sorry, 3,900, not 39,000. 3,900 microfarad. And then for my plus or minus 5.2, I'm going to use 8,200 at 25 volts. That's that. And for my plus or minus 20 volt, I'm going to be using again 2,900 at 50 volts. And these are the screw-on capacitors. As you can see here, all you got to do is just make a hole on the PCB, and with a bit of your PCB, basically a bit of your track showing, little circle, and you put this and you just screw it at the bottom. These are Sprage, basically. These are good brand capacitors. So that's the project that I'm working on at the moment. I just received these parts a couple of days ago, and I did test them individually. Except the counter, the rest of the parts are working perfectly. So I've got the amplifier, I've got the divider and the filter, and the main, which is the oscillator. You can see here, and I'm going to be using, I don't know if I'm going to be using this attenuator or a different attenuator, but as I said, I got the attenuator. So this is basically what you need to make a function generator. Individual parts, and it can do up to 512, 530 megahertz. Perfect. So until next video, that I'll start putting this together and make the power supply and make everything work. Until next time, goodbye.